Okay, we are online. Hello, everybody. This is the first webinar of the year, so we are very happy to be back after a break. This is the webinar number 192, and today we have Brenda Cervantes, that she will talk about the skipper-CCDs. She's a postdoctoral student, postdoctoral position, has a postdoctoral position at Fermilab. She did her PhD at the UNAM, Mexico, and she's an specialist on skipper-CCDs. She is working for more than 10 years on the characterization and the design of part of these detectors. Today she will talk about exploring the dark sector at accelerator with skipper-CCDs. We are very happy to have you here, Brenda, so the floor is for you. Thank you for
Okay. Thank you, Carla, and thank you everyone here. Let me share my screen. Okay, good. Can you see my screen?
Yes.
Great. Well, thanks for the nice introduction. As Carla said, today I will be talking about my current research program, which is exploring the dark sector at accelerators with the skipper-CCDs. So to introduce a little bit the technology, let me tell you what are skipper-CCDs and which is their superpower, as I called. CCDs stands for charge coupled devices. Essentially, a CCD is a pixelated ionization sensor where we have a sensitive volume, usually made of silicon, and any ionizing particle that interacts within that sensitive volume will create electron hole pairs. These free charge carriers, we will collect them near the surface of the device by applying a bias voltage. Then we have some structures at the surface of the device that are electrodes, and by applying different potentials to these electrodes, we are able to create potential wells like the ones that are shown here, where we can store the charge as long as we want and keep collecting free charge carriers if more particles interact, and store the charge. And when we decide to read out, we will be changing the potentials in each of these electrodes to change the form of the potential well. And we can transfer the charge pixel by pixel sequentially towards a last row of pixels, and then horizontally towards the readout stage where we will read our charge. Usually in CCDs, we applied what we call the correlated double sample technique to measure the charge. So essentially, you have here the readout stage of a CCD, and you have a sense node that is actually a transistor that will give you a voltage depending on the charge that is beneath this electrode. So in the correlated double sample technique, we first measure what we call the pedestal signal, the pedestal level, and this corresponds to the potential where the sense node is empty. And then we move the charge towards the sense node, and we measure the potential with the charge, and we call that the signal level. So essentially, the value of our charge packet would be the subtraction of the signal minus the pedestal. These devices are very sensitive. They are very low noise sensor, considered low noise sensors, because the only readout electronic noise comes from the only readout stage, and all the pixels or all the charge packets that are read through this readout stage share the same sense node. So you have a uniform readout noise across all the pixels, and usually this sense node has low capacitance, so you are very sensitive to very small amounts of changes in the potentials. But CCDs have a limit in the noise that they could achieve because they are very sensitive to low frequency noise. Usually the noise values for these standard devices, standard CCDs, reach around 2 electrons RMS. And this low frequency noise cannot be beaten with these devices. So what are skipper-CCDs? So skipper-CCDs have like the same structure of a CCD, but what changes is the readout stage. So in this readout stage, we have what we call a floating gate sense node that enables performing multiple measurements of the same charge packet without destroying it or corrupting it. And therefore, we can make multiple independent measurements with this correlated double sampling technique. And when we finish our charge value, we average all those independent measurements. And with this technique, we can beat the low frequency noise because we are averaging with many small repetitive measurements, the pedestal and the signal, and in some cases they will cancel out like is highlighted here. So it turns out that the noise of this detector, when you do this skipping technique, reduces as 1 over the square root of the number of samples that you take. And if you perform a high number of samples, you will be able to achieve sub-electron noise levels. So here you can see a plot of the noise going down. Readout noise is in the y-axis. The noise going down with the number of samples per pixel. And for example, at 100 samples per pixel, you are already reaching around 0.3 electrons of noise, which allows you to do a precise electron counting because you are able to discriminate the pixels with 0 charge, 1 electron of charge, and it turns out that it stands for a high dynamic range, going up to thousands of electrons that you are able to discriminate how many charges you have. The only disadvantage for certain applications of this technology is that the readout time of these sensors is also proportional to the number of samples that you take. So the readout time grows a lot. But for some other applications, we can deal with those readout times. So CCDs have been used in several fields. One of the important fields is astronomy. So since the 1970s, all the astronomical instruments had as a focal plane a CCD, because as I said, these devices are very low noise. And as they have like micrometer size pixels, they provide a great spatial resolution. Here I put the pictures of two of the most famous astronomical cameras. In the left, you can see the dark energy camera, and in the right, the LSST camera, which actually had its first light last year. And we are having very good images for the astronomical applications. But it turns out that these devices are also sensitive not only to light, but to all ionizing particles. Here you can see a picture of a dark exposure with one of these CCDs. And we can see different tracks from different particles, probably coming from cosmic rays. And as we have like very great spatial resolution, we are able to discriminate each of these tracks based on the geometry. So you can see muons as long tracks, point-like hits, probably from X-rays or alphas, and electrons as wobbly tracks. So these are great sensors also to study particles. with the development of thicker CCDs in the astronomical field to increase the sensitivity to infrared, we were able to achieve enough mass to be competitive for particle detection. I am highlighting here two of the experiments that were pioneering the use of these devices for studying different particles. And as we have very low threshold, this is the silicon band gap, so it's on the order of electron volts, and also very low intrinsic backgrounds, we are very sensitive to feeble interactions. So DAMIC at the Snow Lab, for example, was one of the experiments that are searching for dark matter, and Connie at Brazil is one of the experiments that started using CCDs to detect reactor neutrinos. But what about skippers? So why we want to change to skippers? Well, because skippers allow us to see what is actually right now invisible with the standard CCDs. So here I'm highlighting this image where you can see a dark exposure with a standard CCD, and then, well, with one sample per pixel, this was done with a skipper, but this is like the representation of what you would see with a standard CCD with a noise of 4 electrons. And then we have this exactly same image, but with a noise of 0.2 electrons. As you can see here in the left image, you are not able to discriminate all the less than 4 electron depositions that happen within the background because you are dominated by your noise. And in the skipper image, you are able to see actually a lot of 1, 2 electron depositions that are already there, but you are only able to identify with this sub-electron noise. So essentially, skipper-CCDs allow us to go beyond this noise barrier in standard CCDs and start seeing pixels with 1 electron, which is super powerful for particle searches. So let me go to the next topic of my talk. So which dark sector physics can be explored with skipper-CCDs? Well, let me frame the main application of these skipper-CCDs that has been highly successful, and it is in the search for dark matter. So to motivate this, we know that we live in a dark universe. We have a lot of observational evidence in many space and time scales, from structure formation, from the galactic rotation curves, that give us the hint that there is more matter than what we actually see. In fact, based on these observations, we think that 26% of our universe is composed of dark matter, and we still do not know what it is. So its study is super important, and there have been a lot of efforts to propose many dark matter candidates, and also on the experimental side to try to see if we can get a hint of its nature. We know from the observational evidence some of the properties that dark matter should have. And as I said, we have a lot of candidates that actually span a wide range of masses, from very, very small masses to astrophysical masses, right? But in this talk, I will focus on what we call light-dark matter. So we define light-dark matter for those candidates that are between the EV and the GeV mass scale. And popular light-dark matter models usually consider dark matter to be part of a hidden or dark sector, which is essentially a set of new particles and forces different from those from those that we know, that interact very feebly with the standard model particles through what we call portals that are usually associated to specific mediators. Here I am highlighting one of the most popular portals in these light dark matter models, which is the dark photon portal, where we consider this new vector to be kinetically mixed with the standard model photon. Well, there are different models that are characterized by different mediators and coupling strengths could give different dark matter candidates with different production mechanisms and so on. So how are we searching for light dark matter with the skippers? Well, we use the electron scattering detection channel. Essentially, we live, this is the Milky Way here, we live surrounded by a dark matter halo. And in direct detection experiments, what we do is to try to search an interaction of a dark matter particle living in this halo with particles in your detector. We choose this electron scattering as detection channel because in this channel, a large fraction of the dark matter kinetic energy is transferred to the electron, and you can see detectable signals. In particular, in silicon, as we have electron volt thresholds, we have access to study like dark matter particles of masses as low as a fraction of an MeV, which would leave ionization signals of 1 to few electrons. So in the right plot here, you can see the normalized event rate that different light dark matter particles would leave through electron scattering. Here we are considering 1 GeV and 10 MeV of mass. And as you can see for different light dark matter models, and as you can see, the peak on the event rate is actually either in the first or the second bin, which correspond to 1 or 2 electrons. So we need a detector that are sensitive to creating or identifying 1 or 2 electrons depositions in silicon, and those are skipper-CCDs. So we have a huge program ongoing of light dark matter searches with the skipper-CCDs. In fact, we have been continuously placed world-leading constraints on these light dark matter electron interactions. And as I said, the key is to have the single electron resolution and very low backgrounds. Here you can see pictures of some of the setups of some of the experiments that are searching for light dark matter. We can see here is the Sensei experiment at MINOS at Fermilab, the Sensei at the Snow Lab laboratory in Canada, and the DAPMIC-M setup at the Modane in France. And in the right plot, you can see the current constraints for a specific light dark matter model in this parameter space of dark matter electron cross-section and dark matter mass. And as you can see in the left part of this graph, the constraints from Sensei and DAMICM, which are skipper-CCD experiments, are dominating the field. It turns out that these experiments are gram scale detectors, have gram scale detectors, but are very competitive with some other technologies that are ton scale, particularly the novel liquid detector technologies. So these ton scale detectors are huge, and a good also advantage of the skipper-CCD technology is that it is kind of compact, but what gives its power is the low threshold and the single electron resolution that could compete with these ton scale detectors. So as I said, this light dark matter program search with skippers has been very successful, and so there are future efforts, some of them happening right now, like the DAMIC-M at Modan, reaching about 700 grams of these detectors. Well, the effort right now is to push sensitivity by increasing mass. So when you increase mass, you push your boundaries down to lower dark matter electron cross sections. And the two main efforts, as I said, one is DAMIC-M, and the ultimate effort is called Oscura, which is expected to be at some point at SNOWLAB that would hold 10 kilograms of skipper-CCDs. And the projected sensitivities, as are shown here, will be able to rule out very motivated theoretical models. So I'll talk just briefly about Oscura, because with Oscura we have made a huge R&D effort to develop different things to be able to scale this technology to kilogram size. And within those efforts, we developed a new way of fabricating sensors with a commercial foundry so that we can reach the mass of that Oscura needs to reach 10 kilograms, which would be around 25,000 of these sensors. We also developed for Oscura a new way of packaging the sensors that is compact and that could work for meter size detector. Here you can see what we call an MCM, which essentially is a silicon substrate that holds 16 of these skipper-CCDs. And for Oscura, we needed 1,500 of these MCMs, or in packages of 16, 96 what we call supermodules. Also for Oscura, we did a huge effort developing new readout electronics, because right now we are just reading tenths of sensors, but in Oscura it will be thousands. So we implemented multiplexed electronics so that 256 sensors or channels will be read as one signal only. This is to reduce the complexity of the electronics, and also we developed the Midna ASIC for channel processing, which is essentially a chip that reduces also the footprint of the electronics and makes everything more compact and reduces backgrounds. And also in Oscura, we developed a new way to cool down all the sensors. The idea was to embed all these devices inside an atmosphere of pressurized liquid nitrogen. In 2022, we put together the first demonstrator for Oscura, which is this vessel that actually looks like the Sensei at the SNOWLAB vessel, but we repurpose this vessel to hold 10 prototypes Oscura MCMs and test a discrete version of the multiplexing electronics. In this So this vessel turned out to be the largest skipper-CCD instrument ever built, holding 80 grams. And here you can see a picture of each of these squares would be like a dark exposure of each of these sensors. So it was a success. We demonstrated the sensor packaging, the multiplexed readout, and the performance of both things together. I am mentioning this first demonstrator because this setup, currently we are now commissioning the very same setup at the MINOS cavern in Fermilab, which is an accelerator facility. So why we are moving this to accelerators? Well, this leads me to my third and last topic, which is that can we use skipper-CCDs to probe a dark sector at accelerators? So as you imagine, the answer is yes, but let me motivate a little bit this. So what are we searching for? We are searching for Millicharged particles at this accelerator. So Millicharged particles are essentially hypothetical particles with a fractional electric charge. They do not need to be part of a dark sector, but they arise naturally in different dark sector models that have a hidden U1 symmetry through kinetic mixing with a standard model photon. So if Milli charged particles exist, they would be a direct test of charge quantization, which is super important for all the physics fields. And also could actually constitute a fraction of the dark matter. So as this will have a fractional electric charge, their interaction with ordinary matter is expected to be extremely feeble. So we require ultra-sensitive detectors such as skipper-CCDs for their search. And turns out that these particles could actually be produced at accelerators and also reactors in potentially observable numbers. Here in the right plot, you can see current bands for MCP models with massless dark photon, but the main thing that I want to highlight here is that there are very few constraints on this MeV to GeV mass range, which is the range that we can access with these searches. And it is interesting also because this is the mass range of most of the standard model particles. So it is always interesting to have new particles within that mass range. So which is the current of status of MCP searches with skipper-CCDs? Well, we have performed searches at beam dump facilities. There we have a setup actually at the LHC looking for these particles, and we have done also a search in reactors. But in this talk, I will just focus on the searches that we have at accelerators, which will be the first 2 points. If you want to know more about reactors, maybe some people from the CONI team could give a talk on CONI and the reactors MCP search. But well, let's start with the searches at beam dump facilities. So in this case, we are looking at the NUMMI beam here at Fermilab. So the NUMMI beam is essentially a neutrino beam that has been working since several years ago because it provides neutrinos to many of the experiments here at Fermilab. But in NUMMI, to create neutrinos, we strike a 120 gigaelectron volt proton beam towards a graphite target. Turns out that in this interaction, there are a lot of mesons that are produced, and actually the Millicharged particles can be produced through meson decays, and they would be produced collinearly with the beam. And this is a plot of the number of Millicharged particles expected at the sensei tent. So if you remember the sensei at MINOS setup, so this is a light, it started as a light dark matter experiment to probe that this technology is powerful to search for light dark matter. Turns out that this setup is at the MINOS hall in Fermilab, which is 100 meters underground, and is on the line of sight of NUMI. So this is the number of Millicharged particles that Sensei would see coming from NUMI. And we have in this setup a good shield from cosmics and also a good shield from different higher energetic particles that come directly from the beam, because we have 240 meters of rock in between this place and the target. So it turns out that Sensei was sensitive to Millicharged particles. So using the data collected in 2020 for the light dark matter search, we now search for a few electron depositions between 3 to 6 electrons that are where we have the highest cross section for these kind of particles in the data, and we were able to place constraints on the Millicharged parameter space. Turns out that we were able to constrain a previously unconstrained region in the hundreds of MeV mass range. So this was the first demonstration that the potential that the skipper-CCDs have for performing MCP searches at accelerators. So motivated by these results, we then started the effort that we call now dark bits, which essentially we wanted to repurpose this Oscura first demonstrator, the one that I showed previously, to be able to search for MCPs from NUMI. The idea, the two main goals was first to deploy this setup at the MINOS cavern at Fermilab and operate it there. And then, as we have a multi-layer detector, we are thinking of using tracking for background rejection. As you remember, skipper-CCDs do not have time resolution. They are very slow readout sensors. But if you consider a multi-layer detector and you search for multiple depositions aligned with your beam, you are able to reduce backgrounds a lot. So in the right plot here, you can see the projected sensitivities for dark bits, considering a 16-layer detector with 50 gram day, looking just both like one deposition or multiple depositions. One deposition we call singlet, multiple depositions we call doublet or triplet, and the projected sensitivities that it could reach. And it would constrain several regions of the parameter space that were before unconstrained. Turns out that by using tracking, we enhance sensitivities at higher GeV masses and higher millicharge, the parameter millicharge. Okay, so how is it going? So we completed the installation of the setup of dark bits and MINOS actually last year. Here you can see a picture of my colleague Claudio and myself installing the detectors, installing the electronics, and this is how the final setup looks like. It turns out that it is again the largest skipper-CCD detector in terms of the number of channels that is actually operational, and it has been operational since last year. Here you can see like an array of the detectors that we have. And we are working with more than 200 skipper-CCDs. And I'm glad to say that most of these CCDs are working with single electron resolution. You can see here the pixel distribution, and you can see these different Gaussians corresponding to different number of electrons. So it's a success, and currently the installation was a success, but currently the status of DarkWits, it's in commissioning. So currently we are taking data to characterize the performance of the whole setup of all the sensors, understand all the features that we want to understand, and define the operational parameters, the optimal operational parameters to be able to take data during the NUMION. And we are also developing all of the processing, monitoring, and analysis tools to be able to analyze this data in the future. So the near future plans with DarkWits, we will start at some point this year data acquisition with a lead shield to reduce environmental backgrounds, and we are planning to be ready to take data during this summer that we are expecting the NUMI beam to be on. Okay, great. And then we'll finish with my last setup, that is Moskita, that is actually running at the LHC. So it turns out that Millicharged particles can also be produced at the proton-proton collisions at the LHC. And as these collisions are higher energy, 10 electron volts collisions, we have this allows us to explore heavier masses in the GeV scale. Again, these Millicharged particles could be produced in meson decays and also through Drell-Yan processes with quarks. These MCP searches at LHC has been pushed a lot by the Millikan collaboration. They are working with scintillating technology, but they have identified that a good place to search for these Millicharged particles near the CMS interaction point, which we call the CMS service cavern. This cavern is actually 7 meters underground, so you have a shield from cosmic rays, and is only 30 meters away from the interaction point with a shield of 17 meters of rock in between. This is not in the line of sight of the beam. It is actually almost perpendicular to the beam, but turns out that at these angles, you still receive a flux, potentially observable flux of Millicharged particles. Here you can see the plot that Millikan has made of the expected rate of Millicharged particles, and they would see coming from different processes. So we talked with the Millikan team and they shared the space. So we moved a setup with a skipper-CCD detector to the very exact same cavern. We did that in 2024. So here you can see a picture of Santiago, that is a PhD student at the University of Buenos Aires, with all the boxes that we sent from Fermilab with the setup. And we were there at CERN in the CMS location. And here you can see a picture of the actual cavern where we installed the setup. So this setup is a very small setup. It is essentially one skipper-CCD, 5.4 megapixel skipper-CCD, which is actually very similar or analog to the one that we have in the Sensei at MINOS setup. And it looks like this inside this vessel. We have a LED shield, 2 inches LED shield to reduce a little bit the backgrounds, but essentially we have one CCD. And the main goal, of course, was not to be competitive, but At first, we wanted to understand the low energy backgrounds on site because low energy backgrounds limit our sensitivity. And with those results, the idea was to assess the feasibility of a larger detector. So we have been running this sensor stably and continuously since 2024. We have that data in periods with and without collisions, so that we can compare the rates, the event rates in those periods. And we are using only half of the CCD, 2 useful quadrants, because the other 2, this was a non-science grade CCD, so half of it is broken, but we still have very good images. These are real data of that site. And well, during the 2024, we collected data almost the whole year with just very few periods without data. During the proton-proton collisions, which correspond to the black point here, this is luminosity recorded by CMS. And the colors backgrounds correspond to our runs. And so during those colored backgrounds, we were taking data. So we collected data during proton-proton collisions, during lead-lead collisions, which are the blue points here, and also in periods with no collisions. We collected almost 40 gram days of data with proton-proton collisions and 10 gram days with lead-lead collisions and these luminosities. So with that data, we separated our analysis into regions. First, we focus in the low energy region, which we call, we only studied events that have 20 electrons or less. We did a likelihood analysis to test the background only hypothesis to see if we saw any difference between beam and no beam. And turns out that our rates were mostly consistent with background only. But we saw like a small p-value in the 7 electron beam in the lead-lead collisions, but still this could be still consistent with a statistical fluctuation. So we were aiming to collect more data to be able to rule out this. With these rates, we reported the 95% confidence level upper limits and used the ones from the proton-proton collision period to constrain the MCP parameter space. So here you can see in pink our constraints with Moskita with just one sensor, one skipper-CCD, actually half of a skipper-CCD. And of course, we are not competitive with current bands that are highlighted here in gray. But that was not the idea. The idea was to assess the feasibility of a larger experiment, and with the results from Moskita, considering a 200-gram experiment collecting this exposure, this luminosity, which is the one that we expect for the new run of high Lumi LHC in almost 3 years from now. We will be able to place these constraints in dashed red line. So for the high energy region analysis, which we look at events above 20 electrons, we compare the rates with and without luminosity. Here you can see the event spectra between 0 and 20 kilo electron volts with beam on and beam off. Red is beam on and blue is beam off. And if we perform like the subtraction of those two rates, we are consistent with 0, so we see no excess. But when we see a little bit of higher energies and we perform the subtraction, we were seeing that we had actually a higher event rate after the lead-lead collisions happened. We reported this in this archive paper that actually has been already accepted for PRD, but we are still trying to understand why we see a higher event rate after the lead-lead collisions. So that's the 2025 data. So we resumed the DAQ, well, this last year on April, and we are running, currently taking data continuously since April last year. And the idea for this 2025 period, first is to verify the 2024 results, check if the low p-value in the 7-electron beam was actually consistent with the statistical fluctuation, and try to understand this higher event rate that we see after the lead-lead collisions. We will, of course, increase our exposure and luminosity. And in fact, this 2025, the LHC beam ran for the first time light ion collisions during July. They collision proton oxygen, oxygen oxygen, and neon neon ions, and this will be very interesting data to see. And the data analysis of this 2025 period is in progress, so stay tuned for new results soon. So with that, I end my talk. So my main conclusions are that skipper-CCDs are in fact a powerful technology for detecting feeble interactions. The light dark matter skipper-CCD program has been highly successful, and we are now pushing for the development of more massive detectors within using like the first demonstrators and some setups that we already have in accelerator facilities. We demonstrated that this technology is powerful and competitive to probe, for example, Millicharged particles at accelerators. And with these two efforts that I am leading, Darkwitz and Moskita, we are trying to push to develop the tools and expertise for future dark sector searches at accelerators with this technology or with similar technologies. So stay tuned for new results, and thank you for listening.
Thank you, Brenda. Very nice results. So questions, now we move to questions. So for the audience, you can write the questions in the chat of the YouTube. And I don't know if people that are connected here have any question. I have one to start, but I will let Roberto. Roberto, please.
I just raised the hand. Yeah, Brenda, very nice the webinar. That's very interesting, the topic of the skipper-CCD. But I have one question. When is it possible? I mean, because you said to make larger detector, larger CCDs, but is it possible also to stack different smaller size CCDs to achieve some kind of complementarity or something like that? I mean, this is one question. The real question is, besides the search for this feebly interaction, can be used skipper-CCD for other, I don't know, to measure, let's say, atmospheric neutrinos or other type of particles that tend to be as hard to measure than dark matter, let's say, or the energy range are too different. I don't know.
Yes, so atmospheric neutrinos are a little bit higher energy, and right. So probably the cross section for those particles are kind of low with silicon. So it really depends on the flux that you have, and if that will give you like an interaction you can see, right? So currently with kilogram size detectors, for example, in neutrinos, we are looking for reactor neutrinos because those are kind of MEV energies. and they have like this main interaction that is the sevens, the coherent elastic scattering, that gives you a higher cross section. So you are more sensitive in that way. And also in reactors, you have a high flux, right? In the atmospheric, I think you have less flux, so you will need a more massive detector, which probably kilogram size wouldn't be enough. You will need to probably scale more. But yeah, it depends really on that, on the flux and the cross section in your detector, to see if with kilogram size you are able to see something else. Yeah.
Okay, thank you.
Okay, my question was related to this last data that you take. Did you have the chance to see if this excess after the PV-PV interaction remains there, and what has happened also with the other kind of other element interactions?
Yeah. Well, we are still analyzing the data. Here I'm plotting the single electron rate, and here in this grid is the period with lead-lead collisions. So we actually see like a very slight increase of single electrons, which could hint to a higher event rate. But still we are looking at the data. So the LHC turned off last December. So then vacation coming, so we are still analyzing the data. But yeah, that will be one of our main results and one of the most interesting things to see in this run. And why with the lead-lead? So the lead-lead are heavy ions. These are like just hypotheses, but what we think is that these heavy ion collisions could activate something within the rock or within the surrounding materials of our detectors. And we will see, like we are seeing actually, like decays from those activated materials. But this will give us like a temporal signal. So in the 2024, we caught the data acquisition, and unfortunately, we do not have like a way to see in time if the event rate was decreasing. But the idea with this run that is currently continuous run, the idea is to continue taking data to see if we also see like this temporal variation in the rate to have a hint. With the lighter ion collisions, well, as this will be lower energy, probably we do not see an increase on the event rate, but this is all analysis in progress, so I cannot say much more.
Okay, thank you. More questions? Okay, Roberto?
Yeah, I have a question. I mean, also by looking this plot, maybe I get lost in a part. Is it possible to do with the skipper-CCD measuring the long term? Like, I mean, thinking for possibles to solar modulation effects. I mean, not solar modulation, I mean, annual modulation in the case of dark matter, or this kind of measurement, or is kind of it's not so practical. I mean, I don't know, the background fluctuate too much or something like that to have this kind of continuous survey of the counting rates, let's say.
Yeah, actually, that's something that is done. In fact, in the light dark matter searches, we have performed diurnal modulation because during the day you expect the wind to interact with your crystal lattice in different directions, and that could give a modulation. That's something that is being done. In that the backgrounds are usually well understood and controlled for these very low energy searches. So this is something that is possible, yeah, to see the variation of the rating time. Of course, with the skippers, you usually read out your detector probably in hours. So anything that is a modulation above that time scale, so hours, weeks, or years, it would be possible to see. But if you have a variation, for example, in the case of accelerators, that you have beam on and beam off, but that's in seconds, you are not sensitive to that time resolution. But yes, it's possible.
Okay, thank you.
Okay, we have a question in the chat. It's from Pedro Ventura. He said nice presentation, and he asked if you plan to install MCMs like dark beat sensors at CERN, or you plan to install more skipper-CCDs.
Okay, so yes, that would be pretty good. So right now, the LHC stops this year, probably in June, and it enters a long shutdown of 3 years because they have all the preparations for the high Lumi run, which will start in 2030 probably. So right now, putting more mass in that cavern will only be useful to characterize backgrounds, but we will not have collisions. But the idea is to think about maybe when dark bits is done with a NUMI beam and high Lumi LHC starts, have a similar setup there. Also to test tracking pointing to the interaction point. That would be very exciting. And yes, we are like very interesting. We are interested to make that happen. But currently we have these shutdowns of the accelerator facilities that are that we are constrained with those.
Okay, thank you. Just one more question, curiosity. So the both setup that you present has no shield. So did you operate these setups with some shielding, or you plan to do that? How this affects the sensitivity that you can reach?
Which setup? The
I mean,
Moskita?
or the other one, or Darvit? What are the plans?
Moskita has a small LED shield, 2 inches LED shield, but yeah, it's not a super powerful shield. But this 2 inches LED, actually, we have seen that it reduces the environmental backgrounds by a factor of 3. In dark pits, we currently have no shield, but we also have bought a LED shield, also 2 inches LED shield that we will install at some point later this year. And that will give us a reduction, a expected reduction of 3 times the backgrounds. But that's all what we plan for now. Yeah, it is also like an issue of money and an issue of the design. But yes, that's what we plan. In both setups, we are 70 meters and 100 meters underground, so we have a reduction of cosmic rays that way. But yeah, the current plan is just to install the 2-inch LED shield in dark bits. And yeah, of course, reducing backgrounds increase your sensitivity a little bit.
Okay, thank you. There's no more question at the chat. I don't know if we have any other here. If not, okay, we thanks you a lot, Brenda. We meet again here in 2 weeks for the next Latin America webinar. See you in 2 weeks then. Stay tuned and check the webpage and the media to know about the what are the okay.
Eso es